Long before a part goes into the bath, you must take a few important preliminary steps to make sure that the plating process is ideal. Parts arriving at the shop should be carefully examined for flaws or defects that could interfere with the plating. General tips on pre-plate analysis: make sure the part is clean enough to carefully examine, and do the examination in a very well-lit area. Use a magnifying glass or even a microscope to check the part for minute flaws. You're looking for surface blemishes that could mess with the hard chrome's adherence. Remember that hard chrome tends to exaggerate visible flaws in a part, so you can't plate over a small nick or dent. If you discover a flaw, the part may need to be machined, ground, or polished to eliminate the defect. Bear in mind, though, that grinding means you'll have to plate a thicker layer of chrome to make up for what's been removed. There are some parts whose defects are so bad that it's not worth it to try and save them. In these cases, you need to get in touch with your customer, or whoever it is that wants the part plated, and explain the situation. The pre-plate analysis stage is also a good time to briefly talk about testing the bath, which we also talk about in the bath maintenance module. Testing is usually done according to a schedule, and it allows you to make sure your bath isn't contaminated with suspended solids, an excess of trivalent chromium, or other gunk like chloride and tramp metals. The bath should always be tested while it's being agitated to ensure that you're getting an even sample. Also, the sample should be taken from the center of the bath, using a sample bottle attached to a stick. Once you've taken the sample, remove the bottle and carefully rinse the outside before sending it off for testing. Remember the importance of safety procedures here. Goggles, gloves, and an apron, plus plenty of rinse water, are all imperative for safety. Plus, careful rinsing ensures that you won't accidentally cross-contaminate with another bath. As you know, the point of hard chrome plating is to add a layer of chrome to a metal substrate. But of course that metal part has often undergone assorted processes before it winds up in the plating shop. It's been machined, ground, milled, polished, whatever was necessary to turn a chunk of metal into whatever it is you're plating. These machining processes introduce stress to the metal, and that stress can cause serious problems down the road. Platers must be concerned with tensile and compressive stress in metals. Tensile stress occurs when an object elongates, like a rope in a tug-of-war. Compressive stress occurs when an object is squashed into itself by external forces, like the pillars holding up a building. Both types of stress can occur at the same time, for example when a horizontal object, like a girder, is receiving pressure from above. In that case, there's compressive stress on top as the weight pushes down, and tensile stress on the bottom as the girder bends. Stress accumulates within a part, and chrome plating causes additional tensile stress on metal. If a part has already undergone some strain, the plating process could damage or even fracture it. To help reduce the possibility of this happening, we can do a couple of things to parts before plating. The stress relief bake is a trip to the oven for a few hours. The time and temperature vary depending on standards and what the part is made of. For example, military specifications for hardened steel call for 375 to 400 degrees Fahrenheit for at least 3 hours. This mild heat, mild to steel anyway, softens it and reduces the stress. It's like putting a heating pad on a cramped muscle. Stress relief baking is the most common tool for removing pre-existing tensile stress. Another technique that's often used is shot peening. During a shot peen, the part is placed in a reinforced cabinet and bombarded with small spheres of iron, steel, or glass at very high velocity. This pummeling introduces a more compressive stress to the part, redistributing or offsetting its tensile stress by covering them with more desirable compressive stresses. The blast of shot creates thousands of tiny dimples on the surface of the part, too, evening out stress forces. You often mask a part with tape and wax to protect certain areas and ensure that chrome is only deposited where you want it. It's very important that this masking stays on and adheres completely to the part. Since it'll be soaking in chromic acid for at least a few hours, good adherence of the masking is absolutely necessary. If a part is dirty or greasy, the masking can come undone, resulting in damage or chrome where you don't want it. And even if you're not masking a part at all, grease or other impurities could interfere with plating. So parts are cleaned before they go off to masking. Various cleaning methods can be used, depending on the type and quantity of foreign material present on the part. Common methods of removing grease and oil include vapor degreasing, hot alkaline cleaners, and cleaning machines that use superheated water and caustic chemicals. Parts without heavy grease or soils may simply be hand cleaned using wet volcanic pumice or some other scouring powder and abrasive pad. Another option for cleaning is abrasive blasting, using a high-powered air gun to spray abrasive materials like silicon carbide or glass onto the part. The spray has the consistency of thin sand, and its high speed is very useful for cleaning off light corrosion, scale, or hard-to-remove films. Another benefit of abrasive blasting is that it roughens the surface of the part, which can help the chrome adhere. Platers need to make sure that a part is clean before masking it. Sometimes it may look or even feel clean, but still retain some residue. A trick called the water break test is used to ensure that your part really is spotless. To perform a water break test, dry the part and set it in a vertical position. Then aim a spray bottle containing distilled water 6 inches or so from the part and give it a few squirts. You're looking for what the water does. If it beads up on the surface, the part is still dirty and needs more cleaning time. But if the water sheets off the surface of the part, you're ready to go on to masking. During masking, sections of the part are covered to protect them and prevent chrome deposits. It's pretty rare that an entire part be plated with hard chrome. Usually it's applied only to specific surfaces that need to be resistant to wear and corrosion. So you have to mask or cover the areas that you don't want plated. Masking also protects. Some metals are chemically attacked by pre-treatment chemicals or the chromic acid in the plating tank. By ensuring a good watertight mask, you can protect metals like copper or brass from being damaged by chemicals. So masking is performed either to prevent chrome from depositing on certain areas or to protect certain areas, or both. Generally, it's easier to mask parts where you don't want chrome to form, because a watertight seal can be a little more difficult to manage. Depending on the complexity of the part, it can take a long time for you to mask it. The process also requires great precision and care to ensure that you don't mask even a smidgen of the area to be chrome-plated and don't leave any non-plated area exposed. The tools of masking include tapes, plugs, lacquers, wax, and plastic. What you use depends on the part and your specific needs. Tape is the most common type of maskant and comes in 2 basic flavors, conductive and non-conductive. Conductive tape is typically made of lead or aluminum and distributes current at the ends of parts. Chrome tends to build up more thickly at the ends, so this current redistribution helps minimize that. Non-conductive tape is generally made of bright yellow vinyl and comes in assorted widths. Generally, these tapes are used to mask off larger areas of a part and are often used in combination with conductive tapes. For example, the piston rod is masked with both vinyl adhesive tape and lead tape. During plating, the tape protects areas you don't want covered in chrome. When metallic tape is used, it also helps prevent weird chrome formations on parts you do want plated. Little growths called chrome trees accumulate on the tape rather than the plated area, which will save a lot of grinding when the part comes out of the bath. Wax is often used in combination with tapes, especially when you want to ensure a completely watertight seal on the masked area. Commercial waxes used for this purpose are applied in liquid form, so they're very hot and care is required when using them. Once the wax is dried, it's common to remove tape applied to the very edge of certain surfaces in order to produce a nice straight plating line from the wax. It's also commonly hand-trimmed for precision. Masking is a pain. It's tedious and difficult to get exactly right. It's also one of the biggest sources of error. A mistake means a reject part that has to be stripped and replated. That means double work. Moreover, removing masks requires careful razor cuts and stripping of the maskant piece by piece until it's all off. And of course, all this used maskant must be treated as hazardous waste, since it's been marinating in hexavalent chromium. A new technology called no-mask anodes offers an alternative to tedious masking, especially for shops that plate the same parts over and over. A portion of the Chinook aft shaft is receiving the no-mask anode treatment here. No-mask anodes are custom-made to a specific part and contain a layer of PVC surrounding a carefully fitted lead anode. They're easy to apply. Just snap the no-mask anode on and you're ready to go. Plating racks and fixtures are what hold parts during plating. They can range from pretty simple bars and hooks to elaborate custom-made devices. In general, you'll see racks and fixtures made out of aluminum, since it's cheap, light, and conducts electricity well. Copper is also used at times after being coated to protect it from the acid. Two basic types of anodes are used in hard chrome plating: stick anodes and conforming anodes. Stick anodes are long sticks of protruded lead that are hung in the tank anode bus bars, about 4 to 12 inches away from the part. Conforming anodes are shaped like the part, usually cylindrical, and only an inch or two away. Conforming anodes plate much faster than sticks, plus resulting chrome deposit is more uniform. Good racking can make life a lot easier for a plater, while a bad setup causes many problems. For example, depending on how a part is oriented in the bath, the hydrogen gas released by the reaction may stick to the part as bubbles. That causes missed spots or thin deposits, and it can contribute to brittleness in the chrome. Well-designed racks minimize this by keeping the part oriented in such a way that as little hydrogen as possible can cling to it. Since parts vary greatly in shape and size, consider the difference between the enormous Chinook aft shaft and the small 7980 piston rods, no one racking solution is ideal for everything. Well-designed racks should be easy to load and unload, offer good conductivity, and be strong enough to hold whatever's on there. The hooks are an especially important part of a rack. Usually made of copper, these are what actually conduct current from the tank busing to the rack. Good surface contact is very important here. Fixtures are carried by motorized hoists above the tanks, so workers can easily move them around and lower them down into baths. This mechanism also reduces a plater's exposure to chromic acid when a part comes out. Once the parts are racked, there's just one more step before taking a bath. If you've watched other portions of this course, you've probably already heard about reverse etching, or activation. Etching is an electrochemical process that maximizes the potential bond between chrome and substrate. It's like priming a wall before you paint it. Without the etch step, the chrome will not adhere. There are a couple ways to etch, but the most common technique is to put the part into a chromic acid bath, then invert the polarity of the current. This is called reverse etch activation. During reverse etch, the positive pole of the current is attached to the part, and the negative pole is attached to the anode. Reverse etch takes anywhere from a few seconds to a few minutes, depending on the type of metal the part is made of. Steel parts are commonly hard chrome plated, and during the reverse etch process they will shed some of their iron into the tank. Most shops prefer to install a tank that's entirely dedicated to reverse etching, but you can etch in the same tank you plate in, as long as you understand that the process introduces impurities to the bath. Over-etched or under-etched parts can result in poor chromium adhesion and high defect rate. These problems can become expensive quickly, so great care must be taken when performing the etch process. When a part is properly etched, it will have a dull gray matte surface, free of black flecks or smut. Should black patches appear, it means that some of the carbon in the metal has gravitated to the surface of the part and must be cleaned off with pumice scrub or abrasive blasting before it can be plated. You can find a table containing recommended etch times for various steels and anode types in the handbook. This is where the action happens, where the parts are placed into the plating bath and get their new coat of hard chrome. Most of that action happens at the atomic level, but the plating process is hardly independent of the plater. You have to determine how much chrome to deposit, select a current density, calculate how long to plate the part, and set the rectifier appropriately. Each of these decisions vary based on the type of part you're dealing with and any specific procedures associated with it. The handbook provides a number of examples to help you with determining rectifier busing and calculating thickness and plating times. The key thing to remember now is that you're going for a bright, shiny coat of chrome. Bright deposits have been demonstrated to exhibit greater hardness and wear resistance. If the final deposit is milky, hazy, or burned looking, something went wrong, usually one of the parameters set during the plating process. Temperature and current density are the two most important factors, and they're related. Optimal deposits can be achieved by maintaining a balance between current density and bath temperature, and by ensuring that the part is the same temperature as the bath before you start the process. Current density refers to the amount of current being applied to the part divided by the surface area being plated. It's measured in amps per square inch. Temperature is usually maintained by the heating and cooling systems attached to the tank. So to get the part to that temperature, just let it sit in the bath for several minutes with the rectifier off. To calculate how long a part should be plated, divide the target chrome thickness by the expected rate of deposition. Of course, rate of deposition can be affected by many things, from bath impurities to the type of bath in use. Quality of power and current density are also key factors. Thus, to calculate plating time accurately, you need to know how efficient your bath is. Once the plating is done, the part comes out and post-plating procedures begin. Once the part is fully rinsed, it's time to remove whatever maskant has been applied. This can be a time-consuming process because you need to get all the maskant off. With a well-masked part, that can take a while. Of course, if you're using no-mask anodes, it only takes seconds. Just pop the anodes off and set them aside. That speed can be helpful because you also have to work fast when unmasking. The final step of the plating process comes next, and you only have 1 to 3 hours from the time the part comes out of the tank to get it done. Remember, all discarded maskant must be treated as hazardous waste, and that you should always wear appropriate safety gear when unmasking a part. Once the part is completely free of maskant, it's off to the oven for a bake. So, you're wondering why you have to work fast when taking maskant off a part? Because of hydrogen embrittlement, a phenomenon that terrifies airplane manufacturers and anyone else for whom metal fatigue or brittleness is a life or death issue. During the plating process, water is broken down into its component atoms, 2 hydrogen and 1 oxygen. While the oxygen gravitates toward the anode and isn't a problem, the hydrogen atoms tend to collect on the part being plated, and they're absorbed into the metal. When this happens, the fatigue strength of the part is reduced dramatically, and the metal becomes very brittle. Fracturing, cracks, or stress damage can happen easily to embrittled parts, and high-strength steel, one of the most commonly plated metals, is especially susceptible. To prevent embrittlement, you have to bake out the hydrogen in a hot oven, and you have to do it pretty quickly, before the hydrogen gets settled into its new home and the part is permanently damaged. Military and aerospace specifications usually demand that a chrome-plated part go into the oven no more than 1 to 3 hours after coming out of the plating tank. Bake times vary by part, usually between 3 and 24 hours. Once the bake is over, the parts are ready to go.